Would you still want to be a civil engineer if you knew you'd spend years tracking Excel sheets and writing meeting minutes, hoping one day someone would finally trust you with real design work? I spent years checking spelling mistakes on drawings and writing daily reports because nobody thought I was ready for more. And after 4 years of engineering school, not one professor showed me how to actually build something like this reservoir dam. I followed all the usual advice: be patient, learn from seniors. But all it got me was more paperwork that nobody reads. So in this video, I'll show you how to flip that script by designing a reservoir dam that finally gets your senior engineer's attention without waiting for permission. And hey, I'll even give you a free Excel macro to design a road in minutes. Stick around and I'll show you how to calculate the volume of this lake with a single click, all in under 30 minutes. Let's get started. Here's our site: a small valley, perfect for trapping water and building a reservoir. These red zones you see, those are areas we don't want flooded. Maybe that's where the access road or Farmer Joe's barn sits, who also happened to be our client. Farmer Joe says he just wants a bit of water for his crops, but I have a feeling he's planning a lakeside community and selling waterfront lots. Either way, our job is the same: build a dam that holds water where it should and keeps everything else dry. All right, now let's start with the LiDAR. This is a digital elevation model. Basically, it shows the real ground surface, even under all the vegetation. So you're not seeing trees here, you're seeing the actual terrain. And the best part? This data is completely free. I just downloaded it online, and you can do the same for almost any location. What I'm doing here is checking the water level in built-in 3D, so I can fine-tune where the flooding actually stops. Most Global Mapper users know this 3D view trick, but what many don't know is that you can actually do the same thing right on the plan view. It's a completely separate tool, and I'll show you exactly how to do that. All right, now all I've got to do here is enter an elevation value close to where I want the reservoir surface to be. I'm starting with 320 feet. That's roughly the same elevation as one of those red zone areas nearby. So it gives me a good reference point for how far the water might spread. As soon as I hit apply, you can see the terrain start to fill. This is where the model gets interesting, because you can visually test where the water line sits in real time. If it starts creeping into the red zones, I know the elevation's too high. If it barely fills the valley, it's too low. For now, 320 feet is just the starting point. The idea is to find the maximum elevation first and find the optimum one later. We'll come back and fine-tune it once we decide exactly where to place the dam. That's when we'll balance storage volume, slope, and those flood limits we set earlier. Now, the next thing I'm going to do is to measure potential dam locations. The shortest distance between 2 points is a straight line. And in this case, a shorter line usually means a cheaper dam. So I'm looking for the narrowest spots in the valley, places where we can hold the same amount of water with less construction. But length isn't the only thing that matters. I'm also thinking about access to existing roads, the terrain around the slopes, and how easy it would be to actually build and maintain the structure once it's in place. But don't get fooled by all the parameters. At the end, what matters is to use engineering judgment based on data and field observations. Oh, by the way, I'm seeing the length at the bottom left, which reads about 1,200 feet. Not bad for a reservoir this size, but not the best either. So for now, that's what we got. Now we're drawing the access road alignment. You almost always need a road over a dam, mainly for two reasons. Firstly, you have to cross the valley somehow. Once you flood it, that shortcut's gone, and you definitely don't want to piss off the people stuck on the other side. Second, you need a reliable way for construction flow, a loop that connects to the existing road network so trucks and equipment can move in a circular motion instead of backing up all day. So when I lay out this road, I'm thinking about efficiency and access, a road that serves both the construction phase and the final operation of the dam. I can almost hear you asking, can you find a better spot for the dam or the access road? You probably could, but we're not here to turn this into a PhD thesis that takes 6 months and 5 consultants to justify. Don't forget, The goal here is to get something practical that works, looks realistic, and helps you understand the workflow from start to finish. All right, I finished drawing the access road, and now I'm saving it on a separate layer called road alignment. Keeping it separate just makes it easier to manage later. When we start adding other design elements, I'm also changing the road color to yellow and increasing the line thickness so it stands out clearly against the terrain. That way, even when we zoom in or switch views, you can always see exactly where the road sits on the dam. I've already adjusted the water level to the maximum earlier, but I don't actually know the exact elevation value yet, so I'm going to check that now because whatever that number is, it's going to determine the final dam height. Turns out it's sitting right around 324 feet, which is not a lot different than initial number. Now that we know the water sits at 324 feet, the next step is to trace the reservoir boundary, basically the edge of the lake. Instead of doing it manually, I'm going to show you a quick trick. We'll use a contour line at that same elevation, 324 feet, and it'll automatically trace the shoreline for us. That contour gives the perfect outline of the water's edge and saves you from hand drawing every curve. Once it appears, we can treat it as the water boundary or convert it into a filled polygon later on. I'm going to name this layer maximum flood zone. That simply means this is the highest water level the reservoir could ever reach before it starts overflowing the dam or flooding areas we don't want underwater. It's basically your safety limit, the line that separates what stays dry from what goes under. Looks like water boundary is traced well. You can see how cleanly it follows the valley. That's exactly what we want. I'm doing a few spot checks around the map to make sure none of the red zones fall inside the flooded area. But in this case, everything looks safe. No flooded barns, no angry Farmer Joe. Let me set you up for what's about to come next. You're looking at the dam geometry, the overall shape of the embankment, the cuts and fills, and where the 324-foot water level sits on the cross-section. Up top, I've kept about 30 feet of width, enough for a two-lane road and a strong, stable crest. All right, let's talk about how we'll actually create the dam. To start, we need the center line of the dam, and that should line up with the center line of the access road we drew earlier. There are two ways to do this. First, you can draw a brand new line right across the valley. That's what I'm showing here. The second option is to split the existing road alignment right at the edges of the water polygon. You'll need to do this anyway, because on the right side of the dam, there's no water, so we'll have to split that polygon to keep things clean. Don't worry, even if we split these lines, I'll show you how to combine them back together so your final alignment stays continuous and tidy. Now that we have the dam center line, I'm going to create a buffer of 15 feet on each side of that line. That gives us a 30-foot top width, which matches the width of our access road. Think of this as the crest of the dam, the flat area you'd actually drive across. This way, the geometry of the dam and the road line up perfectly. So when we look at it in cross-section, everything makes sense. Here's a quick reminder of that road cross-section. All right, now let's turn that buffer into the actual dam terrain. I'm selecting the buffer area we just created, and I'll use the flatten to specific elevation tool to set the top of the dam at 324 feet. That's the same as our maximum water level. Next, I'll define the side slopes. Here I'm entering a slope ratio of 0.33 to 1. Now, if you're familiar with Global Mapper, you know the software reverses this ratio. So 0.33 to 1 here actually means a 3 to 1 slope in real-world terms, which is also about 18.5 degrees. Once I apply that, the program automatically shapes the embankment, tying the crest smoothly back into the surrounding terrain. You can already see the new dam blending into the valley, a clean, realistic surface ready for the next step. Let's check this on 3D view to make sure everything is okay. What I typically inspect are any anomalies on the terrain. I don't see any issues, but regardless, always build a habit of checking what you built in multiple ways. Now we're going to look at how the dam changes the site profile. To do that, I'll cut a cross section along the road alignment. But remember, earlier we split that line while setting up the dam center line. So before we run the profile, I need to merge those segments back together into one continuous alignment. That way, the software reads it as a single path across the entire site. Once that's done, I'll open the Path Profile tool. By default, Global Mapper samples every few feet, and that can create tens of thousands of data points, way more than we need. So I'm changing the sampling interval to 30 feet instead. Now here's the interesting part. First, I'll show you the original ground profile before the dam existed. You can see the natural valley shape dropping down through the middle. Then I'll turn on the dam terrain, and instantly you'll see the new profile flatten across the top where the dam crest sits. Now I'm exporting the road profile to Excel so I can process the data later. I'll explain why I'm doing that in just a minute. For now, I'm exporting it as an XYZ file, but instead of keeping that format, I'm saving it as a CSV. It's easier to open, edit, and plot directly in Excel. You might be wondering why I even bother exporting this data. It's because I want to check how this design holds up in the real world, things like vehicle size, road grade, and pavement thickness. Next, we are going to run a macro. Don't be intimidated by it because I'm showing you the easiest and the fastest way to run a macro. First, I start by recording a new macro, and then I stop it right away. We're not actually recording anything. We just need Excel to create the macro entry for us. Next, I open that macro for editing, paste my code right inside, and then save it. That's it. Now it's ready to run. Oh, by the way, if you want to get this code, the link is in the description below. Now that the macro is ready, I'm heading back to the View tab to run it. Here's the one we just saved. I'll select it and hit Run. As soon as it starts, the macro begins asking for a few input values. These are the parameters that control how the road is analyzed, things like slope limits, vehicle dimensions, and material layers. You'll see that it already comes with default settings, but you can easily change them to fit your own design criteria. For this example, I'll keep everything as is to show you how it works out of the box. The only thing I'm going to modify is the pavement thickness. I'll bump that up to 2 feet, which represents the total road structure thickness across the dam crest. That small change gives the macro a more realistic base for calculations, especially if you're modeling heavy construction or maintenance vehicles. Once I hit OK, the code takes over. It processes the elevation data, applies the design parameters, and runs through all the calculations automatically. You'll see the results pop up, and that's where we can start checking how our design performs. Now that the macro is done running, I'm going to save and close the Excel file. If you skip this step, Global Mapper will throw an error during import, so make sure it's completely closed before moving on. Next, I just drag and drop the CSV file right into Global Mapper. A dialog box will pop up. Take a second to check every setting there. It's easy to miss something that can offset your data. Right after that, you'll get the projection window. Here, make sure you select geographic projection and pick the correct units. In this case, we're using feet. Once that's set, hit OK and you're good to go. Now pay attention here. You want to confirm the line imported in the right location and that all the horizontal bends look correct. If it's off even slightly, stop and fix it before going further. Now let's create the road surface right on top of the dam. I'm selecting the line we generated earlier through the macro. That line already carries all the elevation information along its length. Just like we did for the dam, I'll create a 15-foot buffer on each side, giving us the same 30-foot width for the road surface. Next, I'll use the Create Terrain from Feature tool. This time though, I'm not using a fixed elevation like we did for the dam. Instead, I'm letting Global Mapper use the elevations that the surface already has. And that's exactly why we ran it through the macro earlier. The macro gave this line true 3D values. So when we build the terrain, it automatically follows the grades and slopes of the actual road profile. What you get is a fully modeled 3D road surface that blends seamlessly into the dam and the existing ground. Now check this out. When I first learned this, it blew my mind. If you missed it, Go back about 10 seconds and you'll see what I mean. Always keep that Add Measurement Attributes box checked whenever I create or edit a surface. The checkbox automatically tracks all the key data: cut and fill volumes, surface areas, and perimeters. Everything you need to verify earthwork quantities and cost information later on. All right, back to the road. I'm just giving it a quick review to make sure nothing looks off. No gaps, no weird slopes, everything tying cleanly into the dam. Once that checks out, I'll switch to the 3D view so we can see the full picture. The road sitting on top of the dam and the reservoir behind it. Now here's where it gets interesting. The next step is to calculate the reservoir volume. This isn't just a number for the report, it's what tells you how much water the site can actually hold. If it's for agriculture, that volume determines how long you can irrigate. If it's for power generation, it defines how much energy you can produce. And over time, it also tells you the life of the reservoir, because water always carries suspended particles that eventually settle out and reduce capacity. So before we move on, keep that in mind. This single calculation connects design, cost, and long-term performance. Next, we need to create a closed polygon for the water behind the dam. This is what Global Mapper will use to calculate the storage volume. And I'll grab the digitizer tool and draw a line from one end of the dam to the other, closing off the valley so the program knows where the water stops. Once that boundary is complete, it defines the exact area of the reservoir. And that sets us up perfectly for the volume calculation coming next. Now I'm going to create the line that defines the edge of the reservoir. I'll start by tracing from one side of the dam to the other. This will mark where the water stops once the dam is in place. Once that line is complete, I'll save it so we can use it in the next step. Here's something to watch for. The polygon has to be a closed loop. If it's not, Global Mapper will give you an error saying the feature isn't fully enclosed or that there are extra vertices. When that happens, it usually means you've got overlapping segments or tiny gaps somewhere along the boundary. So before moving forward, I'll do a quick cleanup, removing any unnecessary line segments or duplicates that might cause issues later. Once everything looks clean, I'll select all the remaining boundary lines and use the Combine Selected Line Features tool. That merges them into one continuous, closed polygon area. Now we have a clean, watertight boundary, ready to use for the reservoir volume calculation. What I am going to do next is very simple. Let's combine all the line feature for the reservoir into one cohesive polygon. We use Combine Line Feature, as shown here. Since we did a good job of cleaning all the lines, it should work without any issue. And looks like there was no errors, so we managed to do that well. Now that the boundary is clean, I'll use the Advanced Feature Creation tool to turn it into an area feature. Pay close attention to this part. It's what makes the next step possible. This step is important because it's what allows Global Mapper to calculate the reservoir volume. Once the area is created, I'll change its color to blue so it stands out clearly on the map. It's a small visual cue, but it helps separate the water surface from everything else when you start analyzing results. With this in place, we're ready for the next step, finding the optimum water level. This is where things get interesting, because small changes in elevation can make a huge difference in storage capacity, cost, and reservoir life. Now that we've created the maximum reservoir area, let's find the optimum water level. I'm going to generate a new contour line that's 10 feet below the maximum elevation. So instead of 324 feet, I'll enter 314 feet in the Generate Contour Feature tool. Watch this part closely. This line represents how the reservoir behaves under normal conditions, not during full capacity. I'll bring back the cross-section sketch for a few seconds so you can see exactly what that means in the design. The lower contour sits below the dam crest, showing the safe, everyday water surface. The optimum reservoir level is critical. It controls storage, safety, and sedimentation. Keeping the water slightly below maximum helps reduce pressure on the dam and gives you room for flood events. It's the balance between capacity and stability. Next, I'll rename this layer to Optimum Reservoir Level. Then, just like before, I'll convert this contour line to an area and assign it a preset lake color so we can clearly distinguish it from the maximum flood zone. Now we've got both levels, the full capacity and the operational inside one another. That sets us up perfectly for the final volume calculation coming next, where we'll see how much water this reservoir can really hold. Don't miss this because this would be the easiest part of the whole workflow. All you've got to do is go up to the analysis menu, choose pile volume, and Global Mapper does the rest. It runs the math instantly and presents everything in this results table. Total volume, all neatly calculated from the surfaces we just created. I hope this video inspired you to explore what's possible with Global Mapper. Don't forget to download my macro code. Even if you don't use Global Mapper, you can still run it in other tools like Civil 3D or Google Earth to speed up your workflows. And if you want to learn more about site design and Global Mapper, check out this next video where I'll show you how to build a stormwater pond from scratch. Think of it as the mini version of what we built here, a completely different workflow and with fewer angry farmers. And for exclusive Global Mapper tips you won't find anywhere else, not even on my YouTube channel, make sure to sign up for my newsletter. Links are in the description.